Hello and welcome to 8.1. So this unit is on systems of equations, and you actually have seen systems of equations before in Math Foundations and Pre-Calculus 10. The difference was in that class you would have worked with linear systems of equations, so two lines. And here we're working with linear quadratics and quadratic quadratics. So we're just kind of introducing that quadratic element to systems of equations in this class. So just as a reminder, a little bit about systems of equations. So system of a linear quadratic equation would be a linear equation and a quadratic equation that are using the same variable. And the graph of that system would involve a line and a parabola. If you're looking at a system of quadratic equations, that would mean you're looking at two quadratic equations involving the same variables. And so your graph would involve two parabolas. So a solution to a system is a pair that satisfies both equations. In other words, it's a point that can be found, or points that can be found on both graphs. And probably the most important word out of this whole first thing is intersection. So the solution to a system can be found graphically by graphing both of the equations on the same grid and finding out the point or points of intersection. So one question that you might be wondering is, well, how many solutions can we have? Because that seems to be a common theme in this course, depending on what types of functions we're working with. So when we take a look at the systems, if you have a linear quadratic system, that means you have a line and a parabola. You could have this situation here for scenario one, where we have no solutions. As you can see, there's no intersection points. Okay, we could also have, see, we have one intersection point here. So we could also possibly have one solution. And then there could be the scenario where you have two intersection points. So you could have up to two solutions. So when we solve a system that has a linear and a quadratic in it, we might have no solutions, one solution, or two solutions. Is it possible to have three solutions? I don't see how a line could hit a parabola in three different spots. Okay, so the most we could have is two. What if we have two parabolas? So let's take a look. When we have two parabolas, we might have no solution once again. If one opens up and one opens down, and their vertices aren't overlapping, as you can see, we wouldn't have any solutions. It is possible to have one solution. For example, here we have the two vertices being the same intersection point, and it is possible to have two solutions. Now, there's actually one more scenario here, and it's not showing it, but if I have two parabolas and they create the exact same graph, we could have infinite solutions. And I'm not sure why I did not mention that in my notes here. I'm just seeing, yeah, there's no note about it, but it's more rare. You're not going to see it super often, but I'm just going to add it in here that we could potentially have, if you have the same parabola twice, then we could have infinite solutions. Of course, you can't have that when you have a line in a parabola because they're never going to overlap all of their points. But that's another possibility, although we must not encounter very many of those because I didn't even mention it in my typed up notes. Okay, so let's take a look at an example. And here's some that are already graphed for us. So this is Blythe Hartley of Edmonton, Alberta, is one of Canada's best springboard divers. She's doing training dives from a 3-meter springboard. Her coach uses video analysis to plot her height above the water. A, which system could represent the scenario? Explain your choice and why the other graphs do not model this situation. And B, interpret the point or points of intersection in the system you choose. So it's kind of a multiple choice here. So we need to look at which one of these systems, which is a set of two graphs, it represents this scenario. So if we think of a springboard diver, actually the first thing we should look at is what's on our axes. So we've got height and time. So this isn't her physically jumping. It's over time, her height went up and then it went down. Similar to even if you just threw a ball straight up, and it came straight back down, over time, it would look like this because over time it climbed higher and then it went lower over time. So I think we can right away eliminate system B because it doesn't show her motion of going up and then coming back down over time. Where we need to be representing the springboard somewhere on here at the 3 meter mark, and the springboard would not be sloped downward. So we can eliminate system A. I think we're between system C and system D. And so what's the difference? There's only a slight difference between C and D, and that has to do with the y-intercept. So it looks like the y-intercept of the parabola is about there on that graph and about here on this graph. System C would imply that she was hovering above the board and then jumped up. System D would imply she's standing on the board, jumped up, and then went down. So she wasn't hovering, she was standing on the board. So we're going to say system D. Now interpret the points of intersection. So here's one of the points of intersection, and here's another one. Those are the two spots where the line meets the parabola. So the first point here on the left represents her standing on the 3 meter board at the start of the dive. And the second point here would represent she's not standing anymore. She's in the middle of her dive. She's partway through her dive, and she's passing the springboard on her way down. That's when she's passing the board on the way down. Okay, example 2, solve a system of linear quadratic equations graphically. So here we want to solve the following systems of equations graphically and then verify your solutions. Okay, so what we're going to do in this section is, and I believe I said it on the, I'm just going to double check what I had said on the assignment sheet. Usually we use technology in this section, meaning a website or an app, usually something like Desmos. So yeah, if you look at your assignment for 8.1, it says that you can use graphing technology on this assignment. So that's what we're going to do here as well. But before we're ready to put our equations into Desmos, we do want to solve them for y. Which is what they're saying to do here in step 1. If you happen to have a graphing calculator, that's fine. I would say most of us, instead of using a graphing calculator, are probably going to use the Desmos app or website. Then we're going to find the points of intersection, and then we're going to verify our solutions here. So the first thing that we're going to do is solve each of these equations for y. So I want to move the y over to this side, which is quite easy to do. I happened to solve for the y on the right just because it was easier. It was already negative, so I added it to each side. I'm going to do the same thing here. So this becomes 2x squared plus 8x plus 3 equals y. Honestly, you probably should verify the solutions, but because we're using the technology, I'm going to allow you to skip that part. We will do enough checking in the next section to get that skill down. The biggest thing is you have to just make sure that you've rearranged your equations properly. Okay, so I am going to switch my screen now over to Desmos here. Okay, so here we are at the Desmos website, and we're going to graph that example that we were just looking at. So our two equations, the first one was y equals 4x plus 3. So that is the line created there. And then we also have y equals 2x squared. My little pop-up menu is blocked here. Okay, here we go. So we've got 2x squared plus 8x plus 3. Okay, so that gives us our graphs here, and we can take a look at where our intersection points are. So it appears that the two graphs intersect here as well as here. So when I click on that, I can see that one of the solutions is -2, -5. And when I click here, I can see that the other solution is 0, 3. Okay, so those are the two solutions we're going to write in our notes. Okay, so here we are back at our notes. And for that first example here, we're going to record our two solutions, which are -2, -5, and 0, 3. So as you could see on Desmos, these are two locations. So that's why we're using the regular brackets. It's not like in previous units, we've used the curly brackets for set notation because we're listing a bunch of answers. Here we're listing two answers, and each answer is a location with an X and a Y coordinate. Okay, so let's move on to example B and take a look at these ones. So we have the first one, we're going to solve for y. So again, this happens to be a -y here. I'm going to move that over. So I get x plus 1 is equal to +y. Here I have the y on the left and it's positive already. So I'm actually going to move everything else over by adding or subtracting the correct amounts. So that is going to leave me with -x squared plus 6x minus 3. Okay, so now we're going to go ahead and graph that in Desmos. Okay, so here's example B, and the first equation was y equals x plus 1. Oops, I used an s, which actually doesn't really matter. And then our second one was y equals -x squared. Oh. My mouse is going a little bit crazy. Let's try this again. Here, I'm going to take this one off. Hide that. Let's try this again. Y equals -x squared. I think I'm doing too many things on my computer at once here. Plus 6x minus 3. Okay, so here is our graph of our line and our parabola. So let's find our intersection points. So this one is at 1, 2, and 4, 5. So I'm going to go back to my notes here and key that in. So our solutions were 1, 2, and 4, 5. Now, if I were going to check these, this would be my x and my y, and this would be my x and my y. And what I'd have to do is check each x and y in each equation. So I'd have 4 checks. I'd have to check this point in both equations, and I have to check this point in both equations. So there would actually be 4 pieces of your check shown. We're not going to do that in this section, but we're just going to acknowledge that then we would normally check it. Okay, moving on to part C. Again, I want to solve each side for y, so all of this is going to move to the other side here, and all of this is going to move to the other side here. So I'm going to get y equals 2x squared minus 4x plus 5 for the top one, and I'm going to have y equals x plus 4 for the second one. Okay, so now we're going to go ahead and graph that in Desmos. Okay, so our first equation was y equals 2x squared minus 4x plus 5. And our second was y equals x plus 4. So far, these have all been linear quadratic questions. And we're going to go ahead and right away, I can see these are not falling on nice grid lines. And when I see my solutions, they are not nice looking, but there they are. So this is what we're going to write in our answers. I'm assuming that these have been rounded off. These are probably even longer decimals. I think decimals only goes to 3 decimal spots. So I have to assume these decimals may have gone on for a very long time and these have been rounded off. In other words, they're approximations. They're not exact answers. Okay, so we're going to go ahead and write those. And this is actually one of the downfalls of solving by graphing, is that sometimes you cannot read the points very clearly, and therefore you may not actually have the exact correct solution. Okay, so here we're going to try and write down those kind of crazy answers that we just saw in Desmos. and we got 2.281 comma and 6.281. So that was approximately one of the locations. And the other one was 0.219 and 4.219. So not the best, most confident answers that we're giving here. And then can you imagine checking those? That would be a nightmare. So this is one of the downfalls of solving by graphing, is that you do not always get the exact right answers. These look like they've been rounded off. Okay, taking a look at our next set of examples. Example 3 is solving some quadratic equations graphically. So we're going to do the same kind of strategy as what we did last time. We are going to solve each of these for y, and then we are going to graph them in Desmos. And it's basically the same strategy that we used for linear quadratics. Okay, so our first one here, I'm going to move the y, but I also am going to switch the negative 35 over, and same thing here. So we're going to do a little bit of rearranging to get the y's by themselves. So my first, or top one, I'm going to have y equals 2x squared minus 16x plus 35. Excuse me, in the second one, y equals 2x squared minus 8x plus 11. So we're going to go ahead and put those into decimal. Okay, so this time we're graphing two quadratics. So our first one, 2x squared minus 16x plus 35. So there's that parabola. And our second one is y equals 2x squared minus 8x plus 11. Okay, so we can see right away a few interesting things. I'm actually zooming out a bit just to make sure I'm seeing what I think I'm seeing. So these parabolas look like they have the exact same width, but they're just kind of lined up differently. So it looks like these purple and green lines, as I continue looking further and further into the future, they never meet up. So that's telling me that we have one intersection point here. And it looks like that intersection point is 3, 5. Okay, so we're going to go ahead and write that one. So this one seems to only have one solution. So the only solution was 3, 5. Okay, let's go on to part B here. I'm going to solve each of these for y. So my 1 on the top, the y is already positive on the left, so I'm going to move these pieces over to the right. So I will have negative 2x squared minus 16x minus 26. On the second one, I'm going to end up moving this guy over on its own, and then I'm left with x squared plus 8x plus 19. Okay, and so we're going to go ahead and graph those in Desmos as well. You know, I'm actually thinking, if we're using Desmos, I don't know that we actually have to solve for y first. And it's a good habit because it is something that we're going to use as a skill in our next section anyway. But I think the reason we had always said when you're graphing with technology to solve for y first is a lot of calculators have their inputs in that order where you have to have y equals. I'm going to try actually just keying in what we had as our original equation in the order that it was written without me rearranging it. And it should also work and give us our correct parabolas because Desmos can generally handle that. Yeah, so it worked just fine. So if you're using Desmos, actually technically you don't have to solve for y first, but it's not a bad habit. It will help us in future sections anyway. So I'm just making sure I keyed this in properly. 2x squared plus 16x plus y equals negative 26. And then we also had x squared plus 8x minus y equals negative 19. Okay, so we can see right away that we have two solutions here, negative 5, 4 and negative 3, 4. So we could see that our solutions were negative 3, 4 and negative 5, 4. So two intersection points are two solutions for that quadratic system. All right, we're going to go ahead now and graph our last set. And as you can see, they're already solved for y. So we are just going to go ahead and graph those. So our first one was y equals, and then in brackets, x minus 3 all squared. There we go, minus 1. And our second one was y equals x squared minus 6x plus 8. Oh my goodness. So if I don't look at the green one, I can see that the blue one is right underneath it. Same thing if I eliminate the blue, put the green up, the blue is right underneath the green. So these are the exact same parabola, which is something that I had mentioned could happen. And so every single point along these parabolas is a solution. So the solutions are infinite. I could go on forever and ever because this graph keeps rising up and up and up. So we actually have infinite solutions here. So these gave us the same parabola. So we're going to say infinite solutions. All right, we're actually going to skip example 4. And I want to move to example 5 here. So, yeah, I think this is the right one. So suppose that in one stunt, 2 Cirque du Soleil performers are launched toward each other. So those are like gymnasts, acrobats. They're like some of the best in the world. If you have a chance to watch a Cirque du Soleil performance somewhere, go ahead and watch it. I'm sure you can see some cool stuff on YouTube. Anyway, suppose that they're launched toward each other from 2 slightly offset seesaws. The first performer is launched, and then 1 second later, the second performer is launched in the opposite direction. They both perform a flip and give each other a high five in the air. Each performer is in the air for 2 seconds. The height above the seesaw versus the time for each performer during the stunt is approximated by the parabolas as shown. And their paths are shown in a coordinate grid. So we've got 2 diagrams to help us. One is the grid, and then we also have these seesaws showing a little bit of what happened here as well. So A, determine the system of equations that models the performer's heights during the stunt. B, solve the system graphically using technology. And C, interpret your solution to this equation. Okay, so I'm going to do part A kind of up here by this graph because I think it's going to be a little bit hopefully easier to see. And I'm going to analyze the first performer first. Actually, I'm going to switch to green because their graph is kind of in green here. And we need to know a few things. We need to know what the vertex for the first performer is. So their vertex appears to be at 1, 5. And any other point on their graph. And I'm going to choose the easiest point possible, which is 0, 0. And then what I'm going to do is some work like what we would have done in chapter 4 when we were working with quadratic equations, which is to solve for our A value, and then we'll have A, P, and Q all figured out, and we'll have an equation. So in order to solve for A, I must substitute in for the other 4 variables that I know there. And so remember, your 1 and your 5 is going to be your PQ, and your X, Y is going to be your 0, 0. So instead of Y, I'm going to write 0. Instead of X, I'm going to write 0 minus 1 instead of the P, and then that's all squared, and then plus Q means plus 5. So now I have my equation starting to look a little bit simpler. 0 minus 1 is negative 1. Negative 1 squared is just 1. So this is 1A. I don't even need to write the 1. And I end up getting a negative 5 for A. And that makes sense. I should get a negative value. This is a parabola that opens down. So the equation for my first performer is y equals negative 5, x minus 1 all squared plus 5. Okay, I'm going to switch to blue here and do the second performer. Now their vertex is at 2, 5. And I need to choose a point on their graph that's convenient. Unfortunately, 0, 0 isn't a point on theirs, but I'm going to choose something else that's quite convenient, 1, 0. And honestly, I think it's pretty clear these 2 graphs are congruent. I think we're going to get the same A value. So you can do all that work again. I'm going to take a slight shortcut here and say they're congruent. Therefore, A is going to also equal negative 5 on this graph just to save us some time. Okay, so almost the same equation. It's just that our x coordinate has been shifted over. So that actually makes sense when we look at these 2 graphs. Okay, so that is part A. Oh, sorry, I shouldn't have labeled that B. That was all still part A. Part B, we're going to use Desmos to graph. Okay, so this is the Cirque du Soleil word problem. We're going to graph the two equations that we just came up with. So the first one was y equals -5, and then in brackets, x minus 1 all squared plus 5. And I'm just zoomed out a little bit too far to see that. So there we go, found it. And our second one was also starting with the -5 as a value, but this time it was x minus 2 all squared plus 5. So there's our two graphs. And we can see the location where this happens, and it's 1.5, 3.75. We could have maybe tried to look at the original graph they gave us, but I feel more confident in Desmos when I can see that intersection point, and it tells me that exactly because it does pick out key important points like intercepts, vertices, etc. So I know the solution is, I'm fairly confident in it. Okay, so we're going to switch back to our notes. So 1.5, 3.75. So for part B, we had an answer of 1.5, 3.75. Now, really, we should put units on this. The 1.5 was time in seconds, and the 3.75 was height above the seesaw in meters. And truly, back here, even when I wrote my equations, I used y's and x's. I probably should have changed those to h's and t's because of the context of this graph. So my y's really probably should be h's, and my x's really should be t's. And part C says to interpret your solution with respect to this situation. So what does it mean to know that this is the solution here? And to me, that's where and when they high-fived. So they would have high-fived at a height of 3.75 meters at a time of 1.5 seconds. And one of the things that I would say is a hint, if you're trying to interpret a solution, is to look at your units. That's another reason why it was good that we put our units on our answer there. So we can write a sentence, the performers high-fived after 1.5 seconds at a height of 3.75 meters. Okay, so that takes us to the end of our first section of 8.1 on systems of equations. So we're going to, today we solved by graphing using technology like Desmos. In our next section, we're going to solve algebraically, and there's a few different ways we can do that. Okay, so we'll see you next time.